Welcome back, everyone. Welcome back to November. I hope you enjoyed the snow. Who likes snow? Who was excited to see the beautiful snow today? Okay, I like snow. It took me a bit of adjusting yesterday. I was like, oh, it's cold, and I hate being cold. But a warm jacket, we pulled out our mitts, we started listening to some Christmas music, and we're ready for the cold season. So I'll give you 5 seconds to wrap up your conversation so we can begin. And 3, 2, and 1. So the countdown is on until the end of the term. Today we're starting chapter 5, and as you know, that's the last chapter in this course. It's a big chapter. Topic 5.1, where we're starting today, is short, so we might even finish it today, if not on Wednesday. 5.2, 5.1, we're going to be looking at functional groups, identifying them, seeing why they're important. 5.2, we get to see IR spectroscopy, a special analytical technique that can help us identify different functional groups in molecules. It's used as like a detection technique in forensics and science labs to be able to figure out what you've made. When we get to 5.3, we're going to be looking at different hydrocarbons and isomers and conformations. Once we get to 5.3 and 5.4, that's when you want to start bringing your model kit. Okay, so 5.3 and 5.4, when we get there, I will remind you, the model kit, you're allowed to bring it to tests and exams. There are some questions that I still pull out my model kit to solve. So I encourage you to bring it to class as well so that you can get the most out of the experience. The T modules up until the end of the course are already posted. So hopefully you finished up to chapter 4 already. Only 4.1 up to that was on the test. But 4.2 is in the chapter 4 module. Hopefully you got that done over reading week so you're ready just to move on with the new content. If not, make that your goal for this week. Take a moment this week, set aside 10 minutes, think about what your goals are for this course. What are you going to do to the end of the course to reach your goals? What have you learned from test number 2 and test number 1? The answer key is available on OWL. You can check it against your test booklet. What went well? Why do you think it went well? What could you improve? What are some patterns that you noticed in your work that can help you reach your goals for the final exam? And with that, we will jump right in to topic 5.1. And I think you're really excited to see your friends, and I'm glad you are, but I'm going to ask you to hold off on those conversations so that we can get back to chemistry. So why do we study organic chemistry? Chapter 5, we're looking at organic molecules. We're looking at molecules that are based on carbon. Carbon with covalent bonds, often with hydrogen, maybe with nitrogen, oxygen, some phosphorus. Why do we study organic chemistry? Well, it is all around us. Our bodies are made up of organic molecules. The food we eat are organic molecules. Even plastics and a bunch of materials are made up of organic molecules. It's important to understand them so then we can come up with medications for diseases and understand diseases and make new materials and understand how our bodies work. If we look at DNA, deoxyribonucleic acids, it has a bunch of small pieces stacked together to make a macromolecule. As you already know, DNA is known for this double helix with this oxygen-phosphorus backbone and with these pyrimidines and purines that bond together with hydrogen bonds to make up your genetic code. Here we can see thymine and adenine. These 2 nucleic acids have 2 hydrogen bonds, intermolecular forces holding one strand and the other strand together. The sequence of the carbon, nitrogen, oxygen atoms allow it to hydrogen bond in a very specific arrangement. And as you know, cytosine and guanine hydrogen bond as well and bring these 2 helices together. The arrangement of these different atoms to form this organic molecule have the instructions to make your proteins. If there's a miscommunication or a mutation in the DNA, that leads to different proteins that most likely don't function in the way that that protein should. So the DNA makes the code, 3 nucleic acids, tell your body to add a specific amino acid to your protein. The amino acids, as you know, there's quite a few of them, and they all have unique side chains. They all have unique parts in the box over here that have different functional groups that change the way that protein folds, that changes the function of that protein. So for example, in this protein sequence up here, this amino acid is glutamic acid. When you see that ic acid, it often means it has a carboxylic acid functional group. And we're going to be talking about that today. That carbon with a double bond to oxygen, and then that same carbon with a single bond to a hydroxyl group, OH. This side chain makes this amino acid hydrophilic. It likes to hang out with water. It has an electronegative atom, the oxygen atoms, and that changes the electron density distribution in this amino acid. In contrast, if we looked at this valine amino acid, we can see that it's simply an alkyl group. No oxygens, no electronegative atoms. It's hydrophobic. It doesn't like to hang out with water. This changes the function of the protein. It changes the way it folds. And this is the point mutation in the DNA that causes the protein to change and leads to sickle cell anemia. 1 point mutation in the DNA, the instructions to make this protein, changing the functional group on that amino acid from something that's a carboxylic acid to an alkyl group of that particular size, of course, changes the normal hemoglobin folding and function to a sickle cell hemoglobin. It changes the way that it can bind to oxygen, the way that it can carry oxygen in your body, the way that the red blood cell folds in on itself to make that sickle cell and can lead to a lot of illness. One change in that functional group can lead to a completely different function of that protein and the health of that person. So functional groups are very important. When we can understand them, then we can start to learn what's normal, what's not normal, and how can we manipulate it, how can we do good things with these organic molecules. The food that we eat, the breakfast that you had, is also made up of organic molecules. I was chatting with a friend a few years ago, and she was feeding her baby some applesauce. And all of a sudden, she looked at the label and was like, oh no, I can't give this to my baby. It has chemicals in it. It says that they added ascorbic acid. I can't give my kid ascorbic acid. Acid is corrosive, right? But ascorbic acid, what's the other name for that? Vitamin C, right? So vitamin C is often added, and it's found in fruits and vegetables. Vitamin C is ascorbic acid. So you could extract it from an orange. You could synthesize it in the lab. That particular molecule, ascorbic acid, vitamin C, is the same molecule regardless of where you get it from. Of course, if you're eating it with an orange, you're also getting fiber and lots of other components to that orange. Here we have a fatty acid, and this is omega-9 acid. It's a monounsaturated acid, so it has one double bond. And you may remember cis and trans bonds, how we identify those two different types of arrangements around the double bond. We're going to do that later in chapter 5. We can see that this is a cis arrangement. As opposed to trans fats, this would be a cis fat. It's a monounsaturated. It has one site where it doesn't have the maximum number of hydrogen atoms. And this is considered a healthy fat to consume, everything in moderation, and this is a food that we consume. Again, we can see it has that carboxylic acid group and one region of unsaturation, one double bond. Here we have an image of starch. It's like a bunch of sugar molecules attached together, and we can find that in foods like potatoes. So when we think about organic chemistry, we're talking about molecules that have carbon in them, often hydrogen, maybe oxygen, nitrogen, things like that as well. But crude oil is also an organic molecule. It's made up of organic molecules, benzyl groups and alkanes and alkenes and alkynes, all sorts of different organic molecules, carbon in all sorts of different arrangements. Plastics are also made of organic molecules. And there are, as you know, different types of plastics. One here, polyethylene terephthalate. So multiple of these monomers stuck together to make a very large macromolecule with specific properties. This particular type of plastic is really handy for water bottles and rigid plastic materials. It can also be used in polyester. So a whole bunch of molecules stuck together to make ester functional groups through esterification reactions. And that type of synthetic material can be used for clothing. Here we have some polyethylene. So F tells you two carbons stuck together in a long chain. You can have HDPE, high density polyethylene. It's packed in really tight. Or LDPE, low density polyethylene. It's more used for like plastic grocery bags. And it depends on the amount of branching in that plastic material. All of this is organic molecules. All of these things have different functional groups. And the functional groups and the arrangements of these atoms helps to determine their function. So here we have a few more examples, and you have these pictures in your workbook if you flip your page. The first here we have is testosterone, that male sex hormone. You can see it has a bunch of functional groups, and we're going to be identifying these as we go through the course. I want to point out to you that we have some bonds indicated with our wedge. Remember, that's coming towards you. And our, what's that one? The dashed line that goes away from you. In organic molecules, the 3D arrangement in space really matters. So that hydroxyl group, that OH coming towards you, tells you, because this is a carbon atom here, and it must have 8 electrons, or 4 bonds if they're all single bonds. That also tells us that we have a hydrogen pointing away from us. If that hydroxyl group was pointing away from us and the hydrogen was forward, it probably wouldn't work the way it was supposed to. So just one change in the orientation of a bond, one change of an atom can completely change the function of the molecule. Here we have caffeine. We know that's a stimulant. It's in coffee. I didn't grow up drinking coffee, but during my first year chemistry exam, I decided to try coffee because that's what people did. And I shook through my exam trying to fill out this silly bubble sheet. I consumed way too much caffeine and learned a lesson of don't try new things before tests. Sucrose here. We have 2 sugar molecules, glucose and fructose, combined together in a covalent molecule to make a disaccharide, so 2 sugars stuck together. You can see ether groups, so carbon, oxygen, carbon, a whole bunch of hydroxyl groups, OH or alcohol groups. And again, the way these bonds point, the types of atoms that we have, makes the function. We've seen ascorbic acid already. That's our vitamin C. And then we'll finish off here with ibuprofen. Again, we can see that carboxylic acid functional group. We have a carbon with a methyl group pointing towards you. That's a CH3, which tells you you also have a hydrogen pointing away from you because this carbon only has single bonds. Therefore, it's going to have 4 of them. And ibuprofen, as you know, is Advil. So when you're taking different medications, consuming different foods, it's all chemicals. A lot of it is organic. A lot of organic molecules, different functional groups, the arrangement of the atoms determines their function. The way these functional groups are put together changes the way it interacts with your proteins and your cells. So, we're going to have a brief review of some principles of communicating organic chemistry, looking at structures. So I'd like you to chat with the person beside you. Which of the following is or are correct structural formulas for ethanol? Chat with the person beside you and submit your answer. And I'll give you 10 more seconds. And 3, 2, and 1. Okay, most people going for D, 2 of these being correct. Of the A, B, and C, I agree B is okay. I'm not sure what everyone thought A was. Who thought A? No one wants to put up their hands, so I'm not even going to ask you. But let's chat about why A and C are incorrect. Does anybody want to shout out why A is incorrect? At first glance, maybe it looks fine. What's wrong with it? There we go. We didn't label the hydrogens. The 2 carbon atoms, as it's written right now with that line pointing up, implies that there's a carbon atom. When we fill that in, that's way too many carbon atoms for CH3, CH2, OH. If we draw a line, it's assumed there's a carbon atom at the end of the line. When we do the zigzags, because those sp3 hybridized carbons have bond angles 109.5 degrees, remember? Every bend is a carbon, the end of a line is a carbon. If you're going to draw in those lines, you must place hydrogen atoms. Better yet, don't draw the lines and then you don't have to draw in the hydrogen atoms. This molecule here, this is implied that this is a CH3, that's good. This is implied that this is a CH2, sorry, I'll put the C here and draw this out for greater clarity. Hydrogens are implied on carbons, they're not implied on anything else. If the hydrogen is connected to an oxygen or a nitrogen or a sulfur or anything else, we must write that in. So the problem here is that there is not an OH here. So this is what's wrong with this one, and this is what's wrong with this one. So that leaves B, and you may be thinking, but you never draw it that way. I don't, because those Lewis dot diagrams are really annoying. They take a lot of time, you have to draw a lot of dots. We do that to draw in lone pairs. It's still an acceptable way. You learn how to use it, I learn how to use it, but you know that we quickly go to the A-type version or the C-type version using the bent line to draw organic structures. That said, showing all the electrons is a suitable way, and so this would be a correct option. So lots of ways to draw organic molecules. Some of them are correct, some of them are incorrect. Amongst correct, you can have preferences. I imagine most of you don't prefer to draw all the dots, and that's fine. But if you're going to draw it this way, make sure the hydrogens are only implied on the carbon atoms, nothing else. Okay, so that brings us into this review that you have in your notes, reminding ourselves of interpreting these structural formulas. So we're going to take CH3, CH2OH, which is ethanol, the type of alcohol that you can find in wine or beer. We use it for disinfecting as well. So we've already seen this Lewis dot structure. You learned how to use it probably years ago. It's valid, but it takes more time. As you know, we could draw a line to indicate that covalent bond, one line for a single covalent bond. That line implies there are 2 electrons involved. Sometimes 1 electron from each atom, sometimes the electrons came from one atom rather than the other, but it implies 2 electrons. Sometimes we draw in those non-bonding pairs, sometimes we don't. If you're not drawing any of them in, then you don't have to draw them in, unless you're explicitly told draw in the non-bonding electrons or, any such context where you need to draw them in. But then we often try to simplify things. If you're on a computer and you don't want to use a drawing program or pull this out in PowerPoint, we take that first carbon and see the hydrogens that are attached, and that tells us our CH3. Then we take the next carbon, CH2. This is a reminder, we've done this before. And then we have our OH. And again, drawing in those non-bonding electrons or not. We want to make it even simpler. We can use our bendy line design, where we know there's a carbon at the end of the line and a carbon at the bend in the line, and we need to fill in all of the implied hydrogens. Moving forward, we're often going to be using the bottom the bottom three lines, but we need to know how to go back and forth and use these different notations. Okay, so we did something like this before back in topic 3.1. We drew in all the implied carbons and the implied hydrogens. You don't need to redraw this. You have this in your workbook. Remember how to do that. So if you remember, that's awesome. If not, review that tonight. When we're talking about organic molecules, we know it has the backbone of carbon with covalent bonds. That carbon might have 2 regions of electron density. If it does, that means we put in an S and a P atomic orbital. We shook it up in our magic hybridizer and we get out 2 hybridized orbitals, an SP and an SP. One going this way, one going that way. So we're counting regions of electron density as a reminder. So a carbon could have 2 regions of electron density, perhaps a triple bond this way and a single bond this way, with a bond angle of 180. And we learned this when we talked about valence bond theory and VSEPR. When we go to 3 regions of electron density, that means we put in 3 atomic orbitals, getting out 3 sp2 hybridized orbitals. If we have 3 regions of electron density that we're trying to space as far apart from one another as possible, as you know from our VSEPR theory, that means they must be 120 degrees apart, and they'll have that trigonal planar arrangement. They could be single bonds. They could even be double bonds. And now we know that it's the sigma bonds that are 120 degrees apart. That leaves the extra pi orbital, or the extra p orbitals for pi bonding for that pi bond in carbon and oxygen. And then we get to 4 regions of electron density, and we have a question about this. So I'm going to jump in just a second. As a reminder, those lone pairs of electrons take up just a little bit more room. So that's when we get the a little bit less than sign for bond angles. So here we have our first example in topic 5.1. It's a review from chapter 3. The question is, what are the molecular shapes of the 3 structures, and I've repeated it here, that have 4 regions of electron density around the central atom? If we need 4 regions of electron density, remember when we count out the number of atomic orbitals that we put in, if we need 4 regions, that means we need 4 molecular orbitals. 1, 2, 3, 4. That turns into 4 sp3 hybridized orbitals. That means we pick up our tetrahedral VSEPR shape. We can see the bond angles are 109.5 degrees if they're all bonding. So an example of a molecule, the first one here, would be methane. So methane gas that's used for heating up your house, or could be coming out of, oh, my computer is frozen here for a second. Okay, I'm going to freeze this for a second. Chat with the person beside you and identify the 3 molecular shapes for these molecules. Okay, and so on the count of 3, tell me the molecular shape of the first molecule. 1, 2, 3. Indeed, tetrahedral. And you studied this all for our test number 2. And the bond angle, of course, would be 109.5 degrees. Okay, if one of those regions of electron density is a non-bonding pair of electrons, on the count of 3, tell me the shape. 1, 2, and 3. Excellent. Excellent. Trigonal, pyramidal. It's that pyramid. It's not planar. Now the bond angle from hydrogen to carbon to hydrogen is going to be just less than 109.5. Why? Because that non-bonding pair of electrons takes up just a little bit more space, so it presses those hydrogen-carbon-hydrogen bond angles slightly closer together. When we have water, again, just less than 109.5 degrees because those non-bonding electrons are taking up a little more space, which pulls those oxygen-hydrogen bonds, pushes them together, giving us the bent shape. Okay, so with all of that in mind, let's move to functional groups. So we've already been alluding to this, we've been referring to it. Functional groups are, by definition, a sequence of atoms. Maybe it's a single atom, or it could be a group of atoms. But when they come together in that specific arrangement, they have specific chemical and physical properties. As a scientist, when you see that particular set of atoms together in that particular sequence, you can predict some of their chemical and physical properties. You could say that can undergo hydrogen bonding, that can't. That has a polar bond, that's not. That's hydrophilic, it likes hanging out with water. That's hydrophobic, it's like oil, it will separate from water. This will undergo addition reactions. This will undergo esterification reactions. We're not going to cover particular organic reactions in this course. I know that you've covered them in grade 11 and or 12 in high school. You get to cover them in second year organic chemistry at Western. We're not going to specifically cover all the very cool organic chemical reactions. But identifying these functional groups is required to be able to do that. And it's required to be able to do IR spectroscopy, what we're going to be talking about in the next topic, talking about isomers. So we need to be able to identify these different functional groups, but we're not going to be doing organic molecule reactions on them in this course. As we saw at the beginning of class, sickle cell anemia is the result of a mutation, a point mutation in the DNA that leads to a different amino acid being used in the protein. Having something with a carboxylic acid versus an alkyl group completely changes the function. So we want to be able to identify these functional groups and describe why they're important as well. So we've put these into a few categories. You have some really big tables. The end goal is that you can identify these functional groups and describe some of the properties of these functional groups. We're going to start with functional groups and molecules that are simply made up of hydrogen and carbon. Hydrocarbons only have, you guessed it, hydrogen and carbon. Now, this is supposed to be a reminder. You might have spent a few weeks on this, perhaps, in high school. We're going to spend maybe 20 minutes on this. Okay, so it's a review. I'm assuming you know this already, but if not, time to study up on it so that you can identify these. And this is just a nice friendly reminder of these different groups. Okay, so hydrocarbons, we have alkanes, alkenes, and alkynes. They are very similar, but they have different vowels. Those different vowels tell us about the single, double, or triple bond nature between the carbon atoms. We know that also tells us about the hybridization of those carbons. It also tells us what types of organic reactions it can undergo, but we're not going to worry about particular organic reactions right now. So alkanes, this is the type of compound, and then we have the name of the functional group. If the most interesting thing about a molecule is that it has carbon-carbon single bonds. We would call that an alkane. So certain polyethylene plastics are alkanes. The only interesting thing about them is that they have carbon-carbon single bonds. By interesting, I mean other functional groups like an alcohol group or a carboxylic acid group, things like that. If the only interesting thing about it is that it has carbon-carbon single, it would be called an alkane. We could classify the entire molecule by the most interesting functional group. Of course, it gets complicated when you have multiple different functional groups. Sometimes there are rules about how you classify it. We're not going to worry about that for our course. We're going to be looking more at identifying the region of the functional group. So if we have a molecule that has lots of cool functional groups, we'll identify the different pieces of it rather than saying it's this or that. So if it has carbon-carbon single bonds, it's an alkane. If it's a more interesting molecule with all their pieces to it, we could point to just a little piece of it and say there's an alkyl group on a larger molecule that has cool stuff. An alkyl group would be carbon-carbon single bonds. We use alkyl, and then sometimes we tell you about the number of carbons. So we could say a propyl group or a butyl group. Prop tells you 3, but tells you 2, and so on. So sometimes we get specific. A pentyl group. I'm not sure if people use that. So we could talk about the little group, the alkyl group, or we could talk about the entire molecule. Sometimes it's branched. Sometimes it's linear. Sometimes it's cyclic. And we're going to talk a lot about cyclohexanes in the topic coming up. Well, those carbon-carbon single bonds tell us that those carbons are sp3 hybridized. If it only has single bonds, that tells us it's going to have 4 of those single bonds. Well, if a compound has a carbon-carbon double bond, and those carbons then have single bonds otherwise, that is going to be sp2 hybridized. Each of these is going to be sp2 hybridized. And now it's an alkenyl group, if it's part of a molecule, or an alkene, if that's the only interesting thing to talk about. Alkenes tend to undergo addition reactions. You can add stuff to that double bond and add other atoms to each of those carbon bonds through that reaction. So here we have D-limonene. It has 2 double bonds. It has a cycloalkene, that cyclic structure with a double bond, and it has an alkenyl group off of that cycloalkene. So we have alkanes, single bonds, alkenes, double bonds, and alkynes with that triple bond. If it has an alkyne, then that carbon is going to be sp hybridized because it has 2 regions of electron density, triple bond this way and a single bond that way. And of course, it can undergo particular reactions based on that. Alkanes would be considered saturated. They have as many hydrogens as you can possibly add based on the number of carbon atoms. Things with double bonds or triple bonds, those are considered unsaturated. They don't have as many hydrogens because some of those bonds are double bonds or triple bonds. So you can have saturated fats, alkanes, or unsaturated fats, typically alkenes. And then we also have aromatic compounds. And this is when we have a double, single pattern. Often it's in a cycloalkane, but we don't call it a cycloalkane once it has the double, single, because this particular pattern, double, single, allows for delocalization of the electrons. They can be shared really well amongst these 6 carbon atoms. So each of these carbon atoms is sp2 hybridized. Each of them is bonded to hydrogen, for example. Once it's sp2 hybridized, that means it has each carbon has an extra p orbital that was not hybridized. And so you could draw this in with me here. So this one has a p orbital, and all of these p orbitals are orthogonal or 90 degrees. So if the aromatic compound, it's not a cyclohexane, this aromatic group, it's very flat with the carbon double single bond. The p orbitals are pointing straight up and down around this benzene molecule. These p orbitals could share electrodensity this way, double single, or they could share it 3, 4, 5, 6. They could also share those double bonds that way. And that's how we can draw different resonance structures. Moving those electrons. But an even better way to draw it is to draw it with a circle in the middle. Saying, you know, I could draw it double single, or single double, or it's shared so well, sometimes we put a little circle in the middle. So all of those are communicating the same aromatic group. If it's C6H6, then it's called benzene. That's a particular molecule. But if this double single pattern is found in a larger molecule, we call it an aromatic compound or an aryl group, A-R-Y-L. And that tells you that we have that resonance, we have that electron sharing, and that changes its chemical and physical properties. Here we have a bunch of aromatic groups fused together. They're kind of like stuck together and built upon one another. And again, now we have shared electron density across this whole molecule, and it changes its chemical and physical properties and colors and things like that. Okay, so that wraps up our hydrocarbons. Now we're going to move to a set of functional groups that all have a carbon to something single bond that we consider interesting. Z counts for whatever we happen to think is interesting, another element on the periodic table. Maybe X is a halogen, fluorine, chlorine, bromine, iodine. In that case, we call it an alkyl halide, or if it's an aromatic group, so the carbon with the double single pattern, we could call it an aryl halide. So the first part, the alkyl aryl, is telling you about the hydrocarbon, and then we talk about the halide. So we could call it an alkyl halide. Sometimes we get more specific and call it an alkyl fluoride or an alkyl bromide. We use those terms as well. So the halogen or the halide tells you it's coming from the halogen group. So we could call it a halo group or an alkyl halide. So chlorofluorocarbons are an example of a halogen group. Chlorofluorocarbons were used many years ago as refrigerants, and scientists around the world discovered that our ozone layer was depleting. And it was a result of these chlorofluorocarbons. The carbon to chlorine, carbon to fluorine bond is very persistent in the environment. Scientists across the world identified the problem, came up with an agreement worldwide. We reduced our chlorofluorocarbon emissions, and the ozone layer is healing, which is one of the best science stories that we have for identifying a problem and collaboratively fixing it on a global scale. So if you use alkyl halides, a lot of them are used in different organic reactions. We need to make a lot of important drugs and materials that have carbon, halogen, single bonds. But in a lab, you have special organic waste, and then you have an even more special halogenated waste. So if you're doing an experiment, I don't think we do them in this year, but probably next year, there's special containers to collect this type of waste because we can't just put this in an environment. It's very persistent. So if we see a carbon-chlorine bond or a carbon-bromine bond or another halogen, we can immediately identify that as a halo group or an alkyl halide. Now we're going to move to our alcohol. This is when we have a carbon with a single bond to oxygen that then has a single bond to a hydrogen. This R that we're looking at, you can think of it standing for the rest of the molecule that frankly we don't care about. For all of these examples, even though it's the rest of the molecule we don't care about, assume that it must be starting with a carbon atom. So for an alcohol group, it needs to be a carbon attached to an OH group. And this is called an alcohol or a hydroxyl group. So we know about alcohol that you drink. That's only one type of alcohol. We have thousands of other types of alcohols of different sizes of alkyl groups. You can have diols with double alcohol groups. Lots of examples of alcohol molecules. Then we have our ether. This is when we have a carbon to single bond to oxygen, single bond to carbon. So it says the rest of the molecule and rest of the molecule, but the pattern that you're looking for is a COC. That tells you that it is an ether. So COC is what you're looking for. And here you could call it an alkoxy group. You need to know that term. Sometimes we just call it an ether group. Even though it's the whole molecule, it's called the ether when it has this particular functional group, that sequence of atoms. A lot of ethers are used as solvents. Sometimes you can't do your experiment in water because it's so polar. You might do it in a diethyl ether, for example. This molecule here, it's less polar, and you can do different types of chemistry in there. The final one that we're going to look at here is an amine. And when you see the word amine, you know that it has nitrogen in it. And there are 3 different types of amines that you need to be able to recognize. The first is a nitrogen that has a 1 bond to carbon. And this would be called our primary amine. That amine has a non-bonding pair of electrons. As soon as we see nitrogen with single bonds, with no other double bonds in the vicinity, we're just going to see that in a minute, it's called an amine. So if that nitrogen is bonded to 1 carbon, it's a primary amine. If that nitrogen is bonded to 2 carbons, and the remaining bond is a hydrogen, that's a secondary amine. And if that nitrogen is bonded to 3 carbons, again, those carbons can go off and do whatever else they want, then we're looking at a tertiary amine. So my question for you is, which of these molecules and types of molecules can undergo hydrogen bonding with other like molecules? So we're looking at alkyl halides with alkyl halides, or alcohol with alcohol. So chat with the person beside you. Which of these can hydrogen bond? And 10 more seconds. And 10 more seconds. And 3, 2, and 1. Okay, we have votes all across the board here, but barely half went for D, so let's take a look at this. So we want to identify these functional groups. That's like foundation level. It's a nice reminder, but we want to be able to do that so that we can do more interesting things like identifying hydrogen bonding. So the definition of hydrogen bonding is when it's a nitrogen to hydrogen, oxygen to hydrogen, or fluorine to hydrogen covalent bond in one molecule with the NHOHFH covalent bond in the other molecule. So both of those molecules need to have one of those covalent bonds. Alkyl halides, they could have, I suppose, a fluorine, but there is no fluorine to hydrogen bond. There's a carbon to fluorine bond, but not a fluorine to hydrogen. So the difference in electronegativity between carbon and fluorine is not enough to undergo hydrogen bonding. We need to have that fluorine to hydrogen bond, which we don't have here, so this cannot undergo hydrogen bonding. The alcohol, in contrast, does have that OH, and it can certainly interact with another OH and undergo hydrogen bonding. So this can. The ether has a carbon to oxygen and a carbon to oxygen bond, but it does not have an oxygen to hydrogen bond. So it doesn't meet the definition of hydrogen bonding. Therefore, ethers, if we only have diethyl ether and diethyl ether, if that's the only thing we're looking at, there is no oxygen to hydrogen bond to bond there. So then we get to the amines, and this is when we remember we have primary, secondary, and tertiary. By show of hands, who thinks primary amines can hydrogen bond? Put up your hand. I agree, because it has a nitrogen-hydrogen bond, 2 of them for that matter. What about secondary amines? Yes. What about tertiary amines? Not tertiary. Why? Because there's no nitrogen-hydrogen bond. That's where we're going to wrap up today. We'll finish up 5.1 and start 5.2 on Wednesday. Have a fabulous day.